What is the chemical equation that describes the burning of coal? This one, where coal is symbolized by the symbol for carbon, C, with an S in parentheses. What you're going to find out on Tuesday is that that S stands for solid. Solid. Plus O2. G. Gas. That's right. Some people try to pronounce it G. That's not right, because then we would pronounce it jazz. You don't pass jazz, you pass gas. So G for gas. Yields CO2. G for gas. Okay, so on Tuesday we're going to learn what these little abbreviations mean and why they're so important. Does this equation account for all atoms on either side? Look at it carefully.
Yes.
How many carbons?
One.
How many carbons?
One.
How many oxygens?
Two.
How many oxygens? Yes, everything is honky and dory. We have the right number of atoms on both sides. We have the right number of atoms on both sides. What is the chemical equation that describes the rusting of copper? Let's see. Copper, solid, plus O2 gas. And the reason why it's O2 is because there are 7 elements that in their natural state always come as a twosome. Yields Cu2O. Question. Do we have the same number of coppers on both sides of this equation? No. We have 1 copper over here and 2 over here. Is that a problem?
Yeah.
We have 2 oxygens here and only 1 there. Is that a problem? Okay, so it appears that this equation does not account for all atoms on either side. Is it a problem? The answer is yes. If there was a chemistry policeman, you would find that he would pull you over for doing this. He would arrest you because you are now in violation of a very important law. So today what I would like to do is I would like to talk about the law of conservation of mass, the most important law in chemistry. Once again review the idea that reactants are what are reacting and products are what's being produced by balancing these equations. What does it mean to balance them? Okay. So, what does the law of conservation of matter state, and who proposed it? Does anyone know, maybe from middle school? Basically, all atoms that you begin with, you must end up with. Lavoisier, this French scientist by the name of Antoine Lavoisier, said it this way: matter cannot be created or destroyed. It only changes form.
Do we need to write that down?
Anything that has a numerical value to it in your notes, I would write down.
I'm talking about the quote.
Yes, I would write that down. Matter cannot be created or destroyed. It only changes form. Now, who was this Antoine Lavoisier? He was a French scientist that lived in the late 1700s. What's the significance of being French and living in the late 1700s? No, Napoleon came in the 1800s.
I was 100 years old.
Actually, did anyone see Les Miserables?
Oh, it's so bad.
That was the French Revolution, right? French Revolution.
I'd like to sing it. It's quite nice.
All right, so let's learn a little bit more about Antoine Lavoisier, courtesy of Hank Green.
Antoine Lavoisier was pretty fantastic. He was a geologist, a botanist, a biologist, and a physicist. He helped define the metric system, created an international language of chemistry, named hydrogen and oxygen, predicted the existence of silicon, outlined what elements were, figured out how animals extracted energy from food, determined that an element could take different forms upon discovering that both ash and diamond contained pure carbon, published the very first chemistry textbook ever, and there's a reason why the law of conservation of mass used to be called Lavoisier's law. Born into a wealthy family, Lavoisier inherited a massive amount of money when his mom died when he was 5 years old. And though he did get licensed to practice law as his father expected him to follow in his lawyerly footsteps, young Antoine chose science instead. When the opportunity arose to marry a wealthy girl whose father's massive income came from collecting taxes for the French government, he did it, even though she was 13? A questionable decision, though not uncommon at the time. It turned out that the family connections would be his undoing, though not the age of the bride at her marriage. Marie Anne, as she grew older, would become a colleague as well as a wife, assisting Antoine in his experiments and his analysis of the work of others. Indeed, it was Marie Anne who translated Essay on Phlogiston for Antoine, which he ripped to pieces, changing everything forever. Until Antoine Lavoisier started inspecting everybody's work, the prevailing theory of chemical change was that some substances contained an elusive element called phlogiston. By burning these phlogiston-containing elements, they would lose their phlogiston and become new things. Lavoisier took those theories and their research, combined it with research being done elsewhere, and added in his own genius experiments, and then tore the chemical world to pieces with a little thing called combustion. He determined that hydrogen wasn't inflammable air, it was an element. Indeed, he named it hydrogen because it was generated from water, or hydrogenated. And he determined that oxygen was a vital ingredient for combustion and also what would later be known as oxidation, something that we'll discuss quite a lot in this course. By hooking people up to his bizarre contraptions, he determined that burning wood consumed the same amount of oxygen and produced the same amount of carbon dioxide as people consuming food and breathing, thus determining that people, and all animals, are powered by some form of internal combustion. Now, experimenters of the day, I hesitate to call them chemists, noticed that when you burned something, its mass decreased. Like, here's a fuse, and I put it on a scale, and I burn it, and its mass decreases. But Lavoisier determined that if all the particles in gas are collected, like if I burn the fuse inside a closed bottle, the mass stays the same. Stuff remained stuff. You can't lose any. You couldn't make more. This realization, though it seems obvious to us now, and its acceptance by the general scientific community, as far as I'm concerned, was the precise moment at which alchemy ended and chemistry began. Lavoisier's chief contributions and ultimately his discovery of the law of conservation of mass relied on careful measurement and careful thinking, and as you'll see, both of those things are key to success in chemistry to this day. Lavoisier the man was a bit of a dichotomy, having worked as a tax collector and helping to create a literal wall around Paris to assist in the collection of taxes, but also a supporter of the French Revolution as it began. But the enemies he had made with his wall, and by denying certain powerful politicians entry into the French Academy of Sciences, eventually caught up with him as the revolution's lunacy increased. He was beheaded on May 8th, 1794. Lavoisier was pardoned a year and a half after his execution, so that's good. Marie Anne was delivered all of his confiscated belongings and a note of apology, like, "Sorry we killed your husband. Here's all the stuff back." The mathematician Joseph Lagrange said of the event, "It took them only an instant to cut off that head, but France may not produce another like it in a century." It's worth noting, though this isn't really science talk, that Lavoisier couldn't have done any of his magnificently careful measurements had it not been for his enormous wealth. He commissioned the creation of hundreds of pieces of equipment, large and small. Only the system of economic inequality that the French were revolting against made it possible for Lavoisier to do his work. I'll leave you to think on the implications of that on your own.
What Isaac Newton was to physics, Lavoisier was to chemistry. Folks, I mean, he brought chemistry into the modern era. He was brilliant, absolutely brilliant. And maybe, just maybe, if he had lived as long as Isaac Newton, he would have been mentioned in the same breath as Isaac Newton and Lavoisier and Albert Einstein and Stephen Hawking. But he didn't. He got involved in politics, and maybe that's something that maybe that's something that scientists today should also take note of. Don't get involved in politics. Yep, he got his head cut off because of it. Did that last equation obey the law? No. Big fat negatory. Copper was lost. Oxygen was gained. Or the other way around. I don't remember. It was bad. It was bad. How do we fix an equation so as to make it conform to the law? What we're going to have to do is we're going to have to add multiples of the different parts to it, the molecules. We add big numbers, what we call big numbers or coefficients. to the beginning of the molecule in order to have enough of those molecules so that everything is balanced out. When we do this, we say that the equation is balanced. There's some rules that will help us to balance these things. They're not hard and fast rules. They don't always apply. They're just tools that will help us solve these riddles. Here they are. Move from left to right. If you're a Westerner, if you're an Easterner, move from right to left. It really doesn't matter. But since we're in America and we read from left to right, we usually like to go from left to right. Try to, if you encounter any odd numbers like NO3, try to multiply that by 2 so that that 3 becomes an even number. NO6 and 306 and 206 and 206. You'll see what I mean. Sometimes it makes sense to convert water to an alternate way of saying it. Actually, a more realistic way of saying it, and that is calling it HOH instead of H2O. If at all possible, keep polyatomic ions together, especially if you find them on either side of the equation. And these rules will make more sense as you gain experience. Ben knows what we're talking about. He's already gotten a head start on this, right? Always double check your work, because sometimes in your zeal to fix something, you end up breaking something else. So, and one of the easiest ways to destroy all your work is by writing these things incorrectly. By writing these things incorrectly. All right, let's do 4 examples. Some are hard, some are easy. Just generic examples. And then I'll let you loose to learn. This is one of those things where you have to learn through doing it. All right, let us begin. Ben will start us up since he already has some experience with this. And then we'll go back and forth. Sodium. How many sodiums do we have here?
1.
How many sodiums do we have here?
1.
Good. So far, so good. Balanced. How many iodines do we have here?
2.
How many iodines do we have here?
1.
Fix it. Now, some of you are going to say, hey, let's just put a 2 down here. No, you can't do that. Well, what about if you put a 2 right here? No, you can't do that either. The only thing you can do is add a number, which right now there's a number there. It's an understood 1, by the way. You can add a different number right before the whole thing that will change the whole thing. Fortunately for us, it'll fix what we need to fix. Unfortunately for us, it'll break something as well. Because if we add what number here, Ben?
2.
If we add this 2, it applies to the Na as well as the I. So, let's try this again. How many sodiums, Ben?
1.
How many sodiums now?
2.
Yes, you have to use the distributive property. You know the distributive property? 2x minus 1 equals 2x minus 2. Okay? 2 NaI means you have 2 NAs and 2 I's. So, we have broken this. How do we fix it over here?
Oh, you added the number.
Okay, 2 NAs, 2 NAs. How many I's? How many I's? Distribute that through. 2. Okay? This is an understood 1. You don't have to write understood ones.
Can we?
You can if you want to.
Okay.
All right. Maybe that's clear as mud. We got to do it. Divine. How many K's?
1.
How many K's?
1.
Okay, this is a polyatomic ion called chlorate. It would be best if we could just treat chlorate as one thing, ClO3. But the only way that we could do that is if it maintains its identity on the other side. Is ClO3 over here? Okay, so it doesn't help us. So let's do it the hard way. How many Cl's?
1.
How many Cl's?
1.
Okay, so far so good. How many O's?
3.
How many O's?
2.
Okay, we got a serious problem here. This side will always have an odd number of O's. This side, by definition, since it's the only source of O, will always have an even number of O's. That's what I mean by rule number letter B. Okay? If you have an odd number, sometimes it's best to multiply it by 2 in order to even it out. So now how many oxygens do we have?
6.
And how many oxygens do we have here?
2.
So what can we multiply this by to have 6 as well?
3.
Now at this point, if you say to yourself, yay, I fixed O, then you'll be wrong, because you did not follow the last rule, which is always double check your work. Because in our zeal, in Devon's zeal, to fix O, he has now successfully screwed up K and Cl. How many K's?
2.
How many K's over here?
1.
Fix it.
2.
How many Cl's?
2.
How many Cl's?
2.
How many O's? 6. Good job, Devin and friends, who seem to be echoing what he was saying.
Who did you say?
Devin and friends.
Devon.
Devon. All right, here we go. Nicole, how many K's? How many K's? Fix it. Now, PO4 is a polyatomic ion. It would be really nice if we didn't have to go and do the P's and the O's separate. So you ask yourself the question, self, what do you refer to yourself, Nicole? What do you use to refer to yourself? I refer to myself as self. Self, you need to remember to do this. What do you refer to yourself as? You don't talk to yourself? Okay, so Nicole says to herself, Nicole, do I have PO4 on the other side? Ah, okay, so that allows us to keep it together and makes things a whole lot easier. How many PO4s on this side? No, PO4s, the whole thing. 1. How many PO4s on this side? 1. Okay, so the K's are fixed and the PO4s are fixed. How many H's? How many H's? Uh-oh, how do we fix that? How many Cl's? Nope, because you forgot to distribute. How many Cl's? Nope, you forgot to distribute. All right, so Nicole, let's go back and make sure everything's fine. Let's erase all this. How many K's? How many K's? How many PO4s? How many PO4s? How many H's? How many H's? How many Cl's? How many Cl's? Good job, Nicole. Isaac. These are combustion reactions. A hydrocarbon plus oxygen to form carbon dioxide and water. That's a combustion reaction. Okay? Some of them, the bigger the hydrocarbon, the harder these get. Okay? Always try to see if it'll work with one here. But if it doesn't work with one, you may have to try two. All right, Isaac, how many carbons? How many carbons? Fix it. How many H's? How many H's? Fix it. Now, what you need to remember about combustion reactions, Isaac, is that you have two sources of oxygen. So you need to add those sources together. How many oxygens? How many oxygens there? And how many oxygens there? 6 plus 4 is? We're safe. If that was even, if that was an odd number, we'd have to go back and try multiplying this by 2. But we're safe because what times 2 is 10? All right, let's go back and make sure we're right. How many C's? How many C's? How many H's? How many H's? How many O's? How many O's there? And how many more? Which is, congratulations. All right, worksheet 2.4. Make it so. Let's struggle along with it. This is one of those things where you just have to gain experience.